So next we have a local speaker, TC Wu, who's a graduate student in Matt Foster's group. And he will talk about
joint panelist.
Setting up. Okay. He will talk about Meissner and anomalous skin effect in topological superconductors due to surface states.
Right, there's a delay. All right. Hi, everyone. I'm TC from Rice. I'm a grad student in Matt Foster's group. So I would like to start by thanking the organizers for having me today to share some of my recent work on topological superconductivity. So today I first talk about Meissner effect, and then I will talk about the anomalous skin effect. So the main part of my talk would be based on our recent papers, one on PRL and the other one on PRB, done in cooperation with Pavan and readers. So here's my outline. In the first part, I'm going to briefly talk about the material candidates for topological conductors, and then I will talk about how can we use Meissner as a probe for the surface state. And on the second part, I'm going to talk about the anomalous skin effect in wild superconductors. And of course, I have to say something about a popular candidate, uranium ditelluride. And then I will comment on the bulk and surface-to-bulk optical transition. And finally, say something about the effect of these orders and how would that affect our result. So when it comes to topological superconductors, what's in our mind is really a really strong topological superconductor with a fully gapped bulk. So what's interesting about that, of course, is the emergence of the gapless Meissner surface state, which is depicted here. And they're confined at the proximity of the surface. And what's so cool about topological superconductors is that they have the potential to be applicable for building a future quantum computer. So the idea of topological superconductor is very cool. However, nature is not so kind to us because material candidates are relatively rare in nature, but we do have some candidates. So two of them here are the copper bismuth selenide and niobium bismuth selenide, which were also mentioned in Anne's talk previously. So in terms of experimental finding, we have quite a lot of evidence pointing towards pneumaticity, which is consistent with the potential P-wave pairing in these compounds. And from specific heat data, we know that the bulk is likely to be fully gapped. However, so far, we don't have exclusive evidence pointing towards the presence of the Meissner surface fluid. One potential difficulty is that the sample itself is not entirely superconducting. Only a small fraction of it is superconducting. So it is possible that the physical sample, the outermost sample that we are trying to do the measurement, may not be the surface in which the Meissner surface state live in. So the situation in niobium bismuth selenide is more or less the same, although we know that right now it seems that the superconducting fraction is getting better in the niobium case. More interestingly, we have some extra measurement about the change of penetration depth. As we can see here, experimentally, it is indeed seen that we have a power law temperature dependence in the Meissner effect. So how can the Meissner data be consistent with the specific heat? Because we know from specific heat that the bulk is fully gapped. But meanwhile, we still see a power law. So in the following, I'm going to argue that this phenomena is explained by the presence of the surface state in this compound. And as a result, penetration depth can serve as a global probe for the surface state, because Meissner effect is not only sensitive to the outermost surface, but the magnetic field can penetrate up to a finite depth. So his setup, so basically the tools that we are going to use are basically just Maxwell's equation and linear response theory. So if we do a Fourier transformation of the Maxwell's equation, then we got something like this. So basically on the left-hand side, we have the magnetic field as demonstrated by the red arrows here. So the first term on the right-hand side is just the London response. So without the second term, this is what we expect in textbook superconductor. We expect to have an exponential decay. And what's more interesting actually comes from the second term, which encode the parametric response from both the bulk and the surface. So our goal is to solve this integral equation and get the vector potential A. So in solving this integral equation, we'll get some effect of the convolution between the bulk and the surface contributions. So here we go. I just use linear response theory to calculate the response from the surface. So here we get some ugly form factors, which are model dependent, but really the main point here is the T-cube power law dependence here. So the intuition here is that in the system that we are studying, the bulk is fully gapped. So we expect the parametric response to be exponentially suppressed by temperature. However, for the surface, because they are only the gapless excitation in the system, so we expect to get a power law dependence. So roughly speaking, the T-cube dependence originated from 2 copies of the current operator and 1 copy of the density of state, and that's why we get a cube. And one can in general worry about surface to bulk cross term as well, but we argue that although I'm not going to show the details here, they are high order in temperature, and therefore at the very low temperature limit, we just have to focus on the surface part of the response. So after getting the response function, what we have to do is just to plug that into our Maxwell's equation, and then we can solve for the vector potential and get the magnetic field. So again, the first term is the effect without the correction of the surface state. So this is basically just some textbook result exponential decay. And then on the second term, we again get some form factor. But again, the important point is basically just the temperature dependence that we have here, which is T-cube. And based on that, we can compute the change of penetration depth. And indeed, we get a power law temperature dependence, which is because of the presence of the surface state in this system. So the power law temperature dependence is also seen in nodal superconductor, but we want to emphasize that in our system, the bulk is fully gapped. So the bottom line here in the first part of my talk is power law temperature dependence in the penetration depth can be one indicator for the presence of the Meissner surface fluid in topological superconductors. All right, then I'm going to switch gear a little bit and move on to wire superconductor and talk about the anomalous skin effect. So here for wire superconductor, I don't necessarily mean a superconducting wire semi-metal. And indeed, the normal state can be just some simple p-square over 2m fermions. But because of the non-trivial topology of the parent term, in the superconducting phase, we have these wire bonds depicted here. And in between them, we have the gapless surface state, which is shown by the green plane here. So they basically disperse along one direction and they're flat along the other. So roughly speaking, you can think of them as a chunk of 1D chiral Meissner edge mold. And then we just stack them together between the wire bonds. And the situation here we have is analogous to the Fermi arc in wire semi-metal, except I'm plotting here the Bogoliubov-Degen spectrum. So again, material candidates for lateral materials are rare, but thanks to the experimentalist, we right now have quite a lot of evidence that uranium ditelluride is likely to be a wire superconductors. So thanks to the nice introduction by Punchen and Nick, I guess I don't have to talk too much about the experimental findings. So here, let me just recap some of the key aspects. So there have been quite a lot of evidence pointing towards the presence of the point node, and also some evidence for spin triplet pairing. So here are some data for the penetration depth and the specific heat. And we also have data for the curve rotation, which suggests time reversal symmetry breaking. more importantly, the STM measurements by the UIUC group suggest the existence of the Meissner surface state in this system. And there are also surface impedance measurements which suggest the possibility of having a normal surface fit on top of the superconducting bulk. So like I said, for a strong topological superconductor with a fully gapped bulk, we expect to see power law temperature dependence and activation behavior in the specific heat. However, in our case, for wire superconductors, both the bulk and the surface are gapless. So we actually expect to see power law temperature dependence in both phenomena. So as you can see here, we indeed observe some experimental data which is consistent with the power law temperature dependence. But we can, in principle, repeat the analysis that we did for a strong topological superconductor. And what we found is that if the wire points are sitting along one of the crystallographical axes, say the A-axis, which indeed seems to be the case from experiment, then we actually expect the surface to contribute a t-square dependence. And while for the bulk, it is t-square along one direction for the ZZ component of the correlation function, and it is y4 for the YY component of the current correlation function. But there's a recent experimental paper which they claim that they are able to do the measurement of the change of penetration depth for the external magnetic field pointing along three crystallographical directions. And interestingly, along all the three directions, they just see t-square instead of t4. So perhaps this can also be an indication of the presence of the surface state. But you can argue that, okay, perhaps the T4 can be masked by the T-square, and then that's why they don't see it. Okay, so here I'm trying to do another calculation to see if we can find some other signature of the surface based on the optical response. Because right now we have quite a lot of evidence. Well, at least in STM we see some evidence of the surface state. So we can try to do more calculation to see what we can get surface. So despite a lot of effort in DFT, etc., the parent symmetry in uranium ditelluride remains unclear. So here I'm just going to play with a toy model, which is essentially the solid state analog of helium-3A. So this is basically a P plus IP superconductor, as mentioned by the previous talk of James. And in this toy model, it has all the minimal feature that a wire superconductor has. Namely, I have the wire point along the Z direction, and I have the gapless chiral mode as shown by the green plane here. So when it comes to optical responses, we have to consider three contributions. The first one is the bulk to bulk. However, we know that from textbook that the optical conductivity, the power magnetic response of a one band superconductor is actually vanishing for Q going to 0. So we ask, how about the surface to surface? So here we only have one surface state because it is a chiral superconductor, so none is available. So the only one survive would be the surface to bulk transition. And as we'll see, this is the origin, which I call the topological anomalous scheme effect. Okay, so again, here I just employ linear response and Maxwell's equation. On the left-hand side, we have the bulk response, and this is some terms from Maxwell's. And then on the right-hand side, I have the source term, which is basically the source current here that generates the radiation. And then the most interesting term is the surface to bulk response, which originated from these interplay between the surface state and bulk state of this wire superconductor. So in this problem, there are two important limb scales. The first one is the penetration, which characterize how deep the radiation can penetrate into the sample. And the other one is the coherence length, which roughly speaking controls the spatial extent of the surface state. So depending whether the superconductor is type 1 or type 2, the main contribution of the surface to bulk absorption would be originated from the minimal of these two length scales. So in other words, the activation of the anomalous skin effect would occur in the orange region here. So because it is hard to tackle this integral equation, we will just focus on the type 1 or type 2 scenario in which we can make analytical progress in solving this equation. So the approach that we are going to use is basically we can solve for all the eigenstate for this simple Hamiltonian, and then we can compute the response function, plug this back, and then we get the absorbance. So without going into all the details, let me just show you what we got. So here I'm plotting the absorbance normalized in some way with respect to versus the frequency. So delta naught here is the pairing gap. And then I'm trying to tune the parameters of the coherence length. And as you can see here for type 1 superconductor, the YY component, meaning that the external E field is pointing along the Y direction parallel to the surface. And we see that there's a sharp peak located at around 2 delta. And while for the ZZ component, the feature is relatively broad. And the features basically don't change much as we tune the coherence length. So the situation in type 2 is similar. Again, we got a sharp peak at 2 delta for the YY component, whereas for the ZZ component, they are kind of broad. All right, so far we've been focusing on the clean systems in which there are low disorders, but in reality, disorders are unavoidable. So what would they do? So in 30 S-wave superconductors, we know that we have the Meissner result, in which we have a sharp turn on when the frequency is just 2 delta. However, this calculation is only for a 30 system, and actually it doesn't apply in the clean case. If we look at the textbook, there's a derivation for the Meissner, but it's actually kind of hand-wavy, and we can't really generalize that to the case of P-wave. So we try to set up another calculation using the Keldysh formalism. So basically what we did is trying to play with the Q matrix formalism and then try to derive a nonlinear sigma model, and then we cover all the Meissner and stuff. And this is good because this calculation can be generalized for P-wave as well. So here is what we did. So we just restrict ourselves to the self-consistent bond approximation, which is equivalent to the settled bond approximation in terms of the Q matrix theory. And what we got here, what I'm plotting here is basically the scattering rate as a function of the frequency. So as you can see here, for small enough disorders, we have this coherence peak, and the gap in between is gradually being filled as I increase disorders. All right, so using the scattering rate, I can just use Kubo again to compute the optical conductivity. So what we should be focusing on is really the weak disorder case, because disorders are in general bad for P-wave. So here you can see that for very weak disorder, the feature here is reminiscent of the Meissner case for 30 S-wave superconductors. But the difference is that here, because we have Ryle points, which are gapless, so we expect to see something even when the external frequency falls below 2 delta. So as a sanity check, we try to increase disorders and then see what happened. So basically, you can see the gap in between is gradually being filled, and eventually it becomes a thermal metal, which makes sense because for strong disorders, the delta doesn't play a role. So we just recover the normal metal result. All right, so finally, I'm just going to combine everything and then try to plot the overall absorbance. by introducing some small disorders. So here again, for type 1 superconductor, it looks like disorder doesn't do much, and the surface to bulk transition can still survive. In particular, the YY component is more pronounced and with sharp signal at around 2 delta. Whereas for the type 2 case, the effect of disorder can be more important, and as long as disorder is weak enough, we can still see a sharp peak at around 2 delta. Whereas for the CC component, again, the feature is kind of broad. So here is the case for relatively strong disorders. You can see that the signal of the surface to bulk transition is gradually being masked by disorders. So, I mean, if we really want to probe the signal of the surface bulk transition for type 2 superconductors, we need to prepare a relatively clean sample. So that's basically all of my talk. So to sum up, I mentioned to you in the clean case, the surface to bulk transition would give rise to the anomalous skin effect, which is the sole contribution in the clean case. However, once we introduce disorder, the bulk behavior is reminiscent of the Meissner for S-wave case. And when we try to combine the bulk and also the surface bulk contribution, we find that we need a relatively clean sample in order to observe such effect in a type 2 YO superconductor. Thank you.
Thank you. I just wanted to get a clarification first on, let's take the clean case.
Right.
Did you consider which direction is the wave propagation?
Okay.
Normal to the surface. Which surface?
Yeah. So let me
into?
the cartoon again. So so here's my YO superconductor sitting on S greater than 0 in this half space, and then there's E is the external E field, and B is the incident B field, and S is basically the pointing vector.
Where's the chiral axis direction?
So so Y and Z are the is along this plane. So in our system, the Y points are located at KZ equals to minus KF.
Yes.
Right.
Okay, but so you're propagating your wave vector of your electromagnetic field incident on the surface is in what direction? X?
Yeah, so it's propagating along the
propagating into the plane.
S direction, yeah.
And then you're adjusting the polarization of the light, either in plane or out of plane. Is that correct?
Right. So we consider two polarizations. So the E field can either point along the Y direction or along the Z direction. But in both cases, they are parallel to this surface.
Yeah. So I have a couple of references for you. One is that for in-plane propagation for the chiral phase.
Right.
This was studied by me and Hal in 2015. So we looked at exactly this orientation for the chiral state, both the quasi-particle response, but there's an additional response that is the fact that you can excite the time-reversed component of the chiral phase. So if you started with X plus IY, there's actually a Higgs mode at X minus IY. And that has an excitation frequency that is well below the pair breaking edge. So you might take a look at that paper. I can send you the reference.
I see. Thank you. Maybe you can talk after this.
I would also just point you to another paper, which was by Sunke Yip and myself in 1992. And we studied the electromagnetic propagation in the C direction to the chiral phase. So you might take a look at that too.
Sure. Yeah. Thank you for the comment.
Thank you. Thank you for the clear presentation. I have a question about the first part. So in the bulk, you say you have an exponential variation for the penetration depth. That's for the Bismuth 2 selenium 3 intercalated. And then for the surface, it is
So-
cubed. Yeah?
Yeah,
So the question is then, if you measure penetration depth, so how can you disentangle what you,
so
because the surface, how thick is your surface layer? It's
So
in
this
order
is a cartoon. So so the red arrows here are the magnetic field. So I didn't plot the magnetic field profile with the correction of the surface state for the sake of time. So but from that, okay, so I got the expression here. So here's the term without any effect of the surface state correction. This is basically the diamagnetic term from this is just the diamagnetic term, and this is the parametric response correction due to the surface. And in principle, if I plot this profile, then I can see some modulation on top of the exponential decay of the magnetic field. So, but the key point here really is that when we try to compute the change of penetration depth, we have to take into account the contribution of this correction. So from this is the London response, and the bulk, as temperature increase, the bulk is fully gapped. So we expect the change to be, the change due to the bulk would be exponentially suppressed. But for the surface, because they're gapless, so we actually expect to see a power law temperature dependence.
But how can you experimentally access that? Because if you measure penetration depth, you measure kind of average. Yeah, you measure a certain value. So,
sorry, can you say that again?
how can you experimentally access that?
So experimentally, people, so I'm not an experimentalist, but what I know is that people can use the tunneling dino oscillation.
Tunnel diode, yes.
Right. To extract.
You measure then you measure an average, yeah? You don't.
Yeah, so you get, so you can differentiate which is which, but what you can do is you can combine measurement with the specific heat, which is a thermodynamical measurement that is sensitive to the entire sample, whereas for penetration depth, it is only, so we only get the response up to a finite depth, right? Because the field doesn't penetrate all the way down to the bottom of the sample. So in this sense, the penetration depth is sensitive to a particular portion, which is of the size of the penetration depth of the system. So combining with the specific heat data, we can infer the contribution of the surface state. But I agree, this is not a direct measurement, not a smoking gun signature, but it is a suggestion for the presence of the surface state. Okay.
So that's very interesting. Let's imagine we store the time symmetry. So the wild
Oh, the second part, okay.
Merge together graph point and it's the graph. So in that case, you comment whether your results are still valid or how they will change.
So here I talk particularly the wild superconductor, but in principle, you can think about the case with time reversal symmetry as well. Nothing stops you to think about the transition between the surface state to the bulk state in the time reversal symmetric case as well. But here we just didn't do the calculation, but in principle, I would expect you can still get something from the time reversal symmetric case. Because here, I just say, because I only have one branch of the surface state, that's why I don't have to consider the surface to surface transition. But I think if you have another branch of the surface state, and it is possible that you get some, well, you have to consider the overlap between the two surface states, which may indeed actually be orthogonal to each other. Yes. So I would say it maybe depends a little bit on the model that you focus on, but I would expect the surface bulk transition would in general be there if your system is topological non-trivial such that we have the surface state. Yes.
Yeah, this is really, or whatever, my question is about disorder.
Right.
So it seemed to me, and please correct me if I'm wrong, that you are treating homogeneous disorder. And I want to ask, does it matter if, for example, the surface is a lot more disordered? Like, let's say I've got a nice, clean crystal,
Right.
but I have a crummy surface because of preparation or what have you.
Right.
How does that affect your results, if at all?
So here, really, I'm just considering disorder across the bulk of the system. And then I just perform disorder averaging for on-site disorder potential. So what you are saying is, okay, how about I have surface disorder? Then actually, yeah, the short answer is I don't know, because surface disorder in wild systems, I think is still unclear. So I don't have a good answer to that. Because I mean, in wild systems, the bulk is gapless, the bulk is also gapless. As the surface is also gapless. So it's unclear what will happen when the surface is going to merge with the bulk. Yeah, I mean, it's a good question, but I don't have a good answer to that. Sure.
From this picture, we can consider for this system, the disorder first kill the coherent peak and create some in-gap states. Do you have any idea why this happens? Since for 3D system, we do not expect anything localization or something, at least for weak disorder.
So the gapless feature is, well, we can think of this is originated from the gapless feature of the one-node, right? Because I mean, when we just do self-consistent bond, we are basically integrating the, oops, that's my pointer. Yeah, we are basically trying to calculate this diagram, right? So if we have Knoop, then.
But if we do the same calculation for a gapped P-wave superconductor like PX wave, we can also have this coherent peak killed and
yeah, so I mean, even if you do the calculation for S wave, then at the saddle point level, you see the two coherence peak.
Yeah, but for P-wave, at least for gapped PX wave superconductor, the coherent peak will die, and we will also have some subgap states.
Well, is it for a finite size system, or are you talking about?
Change the pairing to from PX P plus IP to PX wave. We can still see some subgap states and the separation of coherent peak.
I see. So so maybe we can talk about that later. But my intuition here is just because these superconductor has point node, and when we try to do the calculation, it is not too surprising to see some non-zero feature below delta naught. But I mean, certainly we can talk more during the coffee break.
Let's thank TC very much again and all the speakers. We will have a coffee break, and so we'll come back at 4:15.